Yeah, start again.
A very good morning to all of you. Welcome to the 9th session of the webinar on machine intelligence in biomedical and health informatics. So today's session was should be presented by Dr. Suganya ma'am, but due to some unavoidable conditions, she can't join today. So again today we have Dr. Praful P. Pai from MathWorks. So I'm giving just a brief introduction of Dr. Praful P. Pai. Praful is with the Academia Engineering team at MathWorks India, where he primarily works with the academia in India towards making STEM education engaging and accelerating research using MATLAB and Simulink. He completed his undergraduate studies in biomedical engineering from Manipal Institute of Technology and his MS and PhD from the Department of Electronics and Electrical Communication Engineering at Indian Institute of Technology, Kharagpur, focusing on non-invasive blood glucose monitoring using photoacoustic. Prior to joining MathWorks, he was a R&D engineer and later a research scientist at National Brain Research Center, Gurgaon, where he worked on developing an MRI brain template for the Indian population. He is passionate about learning, teaching, and research in multidisciplinary domains involving instrumentation, signal and image processing, statistics, and optimization. So now I request Dr. Praful P. Pai to be present here.
Hi, Tripti, and hi, Professor Murugan. Thanks for inviting me again. Yeah. So, just a second. Let me just very good morning to all the participants as well. So, if you just give me a moment, I'll just start sharing my screen and start. So, thank you everyone for joining the live stream again. I'll just, despite I think this being the 5th day, so I am I'm sure many of you have learned a lot over the last 4 days. I hope you find this talk on machine learning useful as well. So let me just share my screen and so hopefully this is visible to everyone. I'll just go ahead and also turn off the camera just to preserve bandwidth. Yeah. So, yeah. So, as I said, welcome everyone to this session on applying machine learning to engineering and science. And thanks again to Professor Tripti Goel and Professor Murugan for inviting me to talk again. I'll be focusing on machine learning in comparison to deep learning, what we had focused on during day 2. So the examples that I have are somewhat related to the biomedical and health informatics domain. And if there's time left, let me just search up examples which are also there, which I can share with you. Right. So so I'd say that please use the comments on the YouTube live stream for the Q&A, and we'll try to address questions at regular intervals. I think in between. And you'll also receive the presentation and code shown. And any information on accessing MATLAB and Simulink or placing requests for trials will be covered at the end of the presentation. As always, in case you have any questions, please feel free to contact me on the email here. Right. So as I said, this presentation, I'll be presenting, but the content in here is developed in association with a lot of other math workers. So it would, so I just wanted to acknowledge the work that went ahead in that. So this is the agenda that we'll be covering. So we'll be introducing you to machine learning concepts and machine learning models. I'm sure most of you might have already learned some machine learning. And in case you have, I hope you find something new here. And in case you're new to the concepts, don't worry, we'll start pretty much from scratch. We'll go over supervised machine learning, wherein we'll look at regression or classification models. We'll look at how we can train machine learning models. You can select one, and we'll also look at feature extraction and feature selection. We'll also briefly overview unsupervised machine learning and see if we have time to cover optimization and automated machine learning, which is like the new trend coming over in the past couple of years. We'll also look at deploying machine learning algorithms at the end and end of the presentation. So this is an example of work. How does machine learning and artificial intelligence fit together, right? So I'm sure like this we covered in the day 2 presentation on deep learning as well. So machine learning is a subset of the general field of artificial intelligence, right? And deep learning is type of machine learning. So MATLAB essentially allows you to kind of do all of these machine learning, deep learning, reinforcement learning, or other applications of these concepts in domains such as predictive maintenance, data analytics, or data science, and so on, right? It has a broad landscape of tools that uh, uh, that covers the entire AI domain. And machine learning is more than just one toolbox. So it's whatever we do in machine learning is connected to your signal processing, your image processing, and also to your statistics and optimization. And it's not just limited to just one toolbox, right? So, uh, so if we look at if we look at how do we get a computer to do what we want, right? So the traditional programming approach what involved using what is known as hand programming or interpreted logic. So you came up with an algorithm which did a specific task depending upon what you wanted it to do, and uh, and basically the computer went ahead and did it. So what happened was you had a bunch of data based on which you wanted to kind of uh, uh, wanted to do some certain task, say analyze a pattern, and you developed an algorithm or a program around it. You fed it with both of these things to your computer and came up with an output. It can be as simple as switching a light on and off if a person is in the room. So maybe taking sensor data from into the computer and writing a program which analyzes that sensor data to see if someone is present or not, and based on that, switching on or off a light, or based on switching on and off AC or a fan depending on temperature inside a room, right? So it can be as simple as that, right? However, the you can't do this for each and every data stream there is. So that's where machine learning comes in, wherein the computer itself learns from data, right? So in this case, what changes is you have your data which you want to analyze or make sense of, and you also have a desired output. What you want to derive out of this data, right? However, what you don't know is how do you go from this data to this output. So how do you map things from a particular data set to a particular output set, right? And that is where the machine learning model comes in. So what essentially happens in machine learning is you find a transformation of some sort between this data and this output. And that transformation is called the machine learning model. So, what is machine learning? So, it uses data and produces a program or a model to perform a particular task. Right? So, let's just briefly look at this task of human activity detection, right? So all of us are familiar with mobile phones and having accelerometers or some sort of GPS and along with some different sensors which provide you acceleration in X, Y, and Z directions, position and on the earth, and so on. Right. So the traditional approach of say detecting what a person was doing based on this accelerometer data could be a handwritten program, right? So if the acceleration in, say, the x direction is greater than a particular threshold, then you assume that the person is sitting. Or if acceleration in other F, Y, and Z directions are, are more than or less than a particular threshold, they're doing something else. Yeah. So basically, what you come up with is a set of equations or formulae which translate this algorithm or this uh, translate the data which is being fed into the algorithm into a set of decisions, whether the person is walking, whether the person is climbing up the stairs, he's sitting down, he's lying down, or just simply standing and not moving at all. Right. However, as you can sense, it's a very complex task, right? So in the machine learning approach, what we're trying to do is we're just trying to map this input data, that is the accelerometer readings, to outputs. So which is one of these, say, 5 or 6 states, whatever we want to classify it, right? And our model is basically our machine learning algorithm, which takes in sensor data and your outputs, right? So I hope this makes it relatively clear. So machine learning algorithms are basically a set of computer algorithms that improve automatically through experience. So this is the typical machine learning definition provided by Tom Mitchell in his textbook on machine learning. Right? So if you're interested, you can visit. You can easily access this book on his website. And machine learning is everywhere, right from something like speech recognition or object recognition, health monitoring, wherein the solution is too complex for handwritten rules, like we just saw, and there are very complex non-linear relationships between your data and your output, right? Or there can be a problem wherein the solution needs to adapt with changing data. For example, in weather forecasting or load forecasting or stock market prediction, wherein constantly new data is coming in to the system, and you have to work with that data and adapt to changing trends, right? So your machine learning model itself needs to be updated as more and more data becomes available. It cannot be a static model. So in this case, if you were writing hard-coded uh, algorithms, then your algorithms will not really update as new data or new situations emerge, right? So your model needs to be able to recognize these situations and then uh, work on improving itself, right? Or there can be the need for models where the solution, the machine learning model, needs to scale. So, for example, in something like an IoT analytics case or a taxi availability case, in case of say something like Uber or an Ola uh, taxi cab, wherein uh, uh, there are a large number of uh, options available, and our machine learning model should be able to work just as well with one taxi available in your vicinity uh, versus 10 or 20 taxis available in your vicinity, right? So so the machine learning model needs to be able to learn efficiently from very large data sets and also operate on large data sets with minimal delay, right? Uh, so, so what we'll do is, yeah. So just to highlight, the wide variety of uh, areas wherein it is used. You can see something like machine learning being used to improve some in fighter fleet performance in the aerospace sector, to forecasting, energy forecasting in the energy sector, or portfolio allocation in the finance sector, or building energy optimization, or something like predictive maintenance in the industrial automation sector. Right? So all of these are examples of wherein MathWorks tools, MATLAB and Simulink were used for uh, doing the machine learning task. And these links will take you to the particular user story. So in case you belong to any of these sectors specific, uh, any of these particular sectors, then you should definitely check more through these links. All right. Also, to contrast how it uh, appears in comparison to deep learning, right? So in case you didn't attend the day 2 session on deep learning, so deep learning performs end-to-end learning, right? Wherein the deep neural network automatically learns the features and representations and tasks in the weights and biases present in the network, right? Whereas in machine learning, you are doing some amount of feature extraction, which uh, leads you to a set of features which you feed into the machine learning model. Right? And that machine learning model uses it to yeah. And how does machine learning and deep learning contrast? Like, what should you go for, right? So this is again something that I covered that day. So if you have a good set of hardware and lots of data to perform your task, then possibly deep learning is the way to go. However, if either of these things is absent, then possibly machine learning is techniques might be better suited. Also, another thing which isn't covered in these two is maybe the complexity of the problem. So if the problem is very complex, uh, then it might be a better option to go with deep learning. But if it's a simpler problem, like if you are able to kind of, as a human, identify how you can process a particular signal and arrive at a result, then possibly machine learning models which use some statistics or some characteristics of the signal, uh, the machine learning model will be able to do that as well. So in case it's a very tractable problem, uh, you can always use machine learning models to kind of implement that. All right. So let's look at a typical machine learning workflow. It's again very similar to the deep learning workflow that we had seen that day. So the first step is accessing and exploring data. This could be in the form of files from databases, from different hardware sensors which are available with you. So it can be something like financial data from a database, or from a stock market database, or energy use data from, say, a power sector utility. Yeah. You have to pre-process this data. That is, you have to do some sort of outlier removal. You have to do noise cleaning, data reduction, transformation, and so on. And you have to extract some set of features from this data. So these can be as simple features as uh, taking out, maxima or minima from the data, or as complex as uh, doing some sort of spectral analysis and deriving features out of that. Right? The next step will be developing the predictive model, wherein you are looking at creating a machine learning model from this data. Uh, and similar to how you do for deep learning networks, here you do parameter optimization on these networks. So, as in, you change various options or various characteristics of the model itself to see which model or what variant of a particular model performs better. We'll see when you'll probably understand this better when we see one in action, and then maybe this will help understanding this concept. And finally, similar to any machine learning task, we need to perform validation. Right? So there needs to be some sort of model validation which is required for the machine learning. And finally, once we have developed our machine learning model with suitable accuracy, we need to integrate it into other systems. We can either deploy our machine learning model as simple desktop apps, which can be used by the end users, or deploy it to enterprise scale systems wherein it works with a wider variety of platforms, or it integrates with other platforms and for taking in data or giving out results to. Or it can be used at with embedded devices or in hardware for something like, say, an edge computing problem, or wherein you have very little hardware resources for your computation. So your final machine learning model is uh, run on an edge device to perform one very specific task. Right? And using MATLAB and Simulink, you can iterate on all four of these steps until you kind of realize optimal model. Right. So let's briefly review different types of machine learning algorithms. Right. So we'll basically classify machine learning algorithms based on the type of learning, and then look at the categories of algorithms. Right. So machine learning can broadly be branched into supervised learning and unsupervised learning. Right. So supervised learning mainly involves developing predictive models based on both input and output data. So when both the input data and output targets are available to us, we can uh, come up with a mapping directly. So that is why we can basically supervise how the model performs itself, whether it is mapping the correct input to the correct output. And that is where the supervision aspect comes in. Right? And supervised learning algorithms can be broadly classified into regression or classification algorithms. So if you're predicting a value or a numeric output, then you're using a regression algorithm. For example, a load forecasting problem wherein you are trying to predict what amount of energy will be consumed from the grid uh, at a particular point in time during the day, and trying to balance your energy generation from a variety of sources using that. So that is particular load forecasting. If you look at the medical domain, then maybe predicting your blood glucose levels based on your past blood glucose readings. That is very similar to this approach. So instead of measuring blood glucose levels at particular points in time, we can very easily predict blood glucose levels varying throughout the entire day, and then using that prediction, look at how we can adjust the medication given to a particular patient so that blood glucose levels do not cross a threshold. All right. The other thing is a classification problem, right? Wherein we are trying to uh, train a classification model to distinguish between two separate classes or two separate categories, or two or more separate categories. So the human activity detection is a good example here, wherein you are trying to kind of take the accelerometer readings and trying to classify it into into multiple states. If you are doing the same with a ECG or an electrocardiogram, you can possibly, classify it into two categories: normal versus abnormal. Or you can also go ahead and see if you can classify into multiple categories, like look at what specific abnormality you can predict, right? So all of these are things that you can do with machine learning models. The other aspect is unsupervised learning, wherein you only have a set of input data, which is you're trying to essentially discover an internal representation of the data, or you're trying to discover uh, what you can, what patterns or what uh, inherent classes might exist in a particular data set, right? So in that case, you can look at clustering as a particular algorithm, right? So you do not really have any sort of outputs or any sort of categories which your input will map into, but you'll often see that much of your data can be grouped or clustered together, right? So if you just look at, say, the engine speed versus vehicle speed shown here, right? So if I'm sure many of you drive a vehicle or or a car of your own. So uh, if you see, on the x-axis there is engine speed, whereas on the y-axis there is vehicle speed, right? So the engine speed in rounds per minute varies, and all of these points are individual measurements, right? So it varies. The engine speed varies from 1,000 RPM to something like 4,000 or 5,000 RPM, whereas vehicle speeds in miles per hour or kilometers per hour varies from something like 0 to 80. Uh, yeah. So if you had all of these dots as assume all of these dots were black and not colored like I'm showing, right? So you could see that there is a band of dots here wherein engine speed, while engine speed increases from something like 1500 to 3500 or so, the vehicle speed barely goes up from something like 5 miles per hour to 10 or 20 miles per hour, right? The engine speed does not increase as much. The vehicle speed does not increase as much. So in other cases, say in the fifth cluster over here, you'll see that the topmost cluster, you'll see that as engine speed increases from 1500 to 2000, the vehicle speed itself increases more, almost by 10 miles per hour, right? So uh, if you are just given these as black points, us as humans will be able to see that there are these five classes or categories which are formed over here, and those five classes belong to each of the gears of the vehicle, right? So at a lower gear, not the entire power of the engine is not transmitted to the wheels of the vehicle by the gearbox, whereas as you go higher, as you shift to higher gears, the more of the engine power is transmitted to the wheel, right? So analog in the medical domain can be something like, or in the healthcare domain can be something like, say you're measuring systolic and diastolic blood pressure for a group of patients, then you may get three different categories here, right? So there might be a group with low blood pressure, there might be a group with normal blood pressure, and there might be a group with high blood pressure, right? So in case you were not given any outputs to map it to, you can still cluster these into these three categories, right? Yeah. So let's move ahead. So as I said, a typical machine learning or deep learning workflow has these four steps. Yeah. So let's look at the how the machine learning model actually learns. Right? So the first step is importing the data set. Right? So your data set, the data set that you import, or on which you have to do your machine learning or develop your machine learning model, is initially divided into training and test data. Right? So on the training data, it's similar to what you do with say when teaching a particular subject. You train your machine learning model on their training data, and you validate whether your machine learning model has actually learned the particular task, right? So these steps involve something like, pre-processing the data, so either filtering it to remove noise, doing some sort of feature extraction, like saying finding summary statistics, uh, doing some sort of feature engineering, like you may want to do a particular feature that and every time you kind of create a model, or every time you maybe train a particular model over using the training data, you also need to validate whether it has actually learned the task uh, that it that you want it to. So think of this as an analog to learning in a class, right? So if you are, say, teaching a particular subject to a class of students, so what you do is you have uh, a bunch of problems which you teach in the class. So that is your training, or say a bunch of concepts that you teach in the class. The students learn this and they can map a particular problem to its solution. Now, there are a bunch of problems which you haven't shown to the class, which will appear on, say, something like the end semester examination. That is your test data, right? But you also want to see whether the students or the class has actually learned the concept, right? So what you do is you actually try and test the class in between at regular intervals through something like a class test or a unit test, and not simply at the end of the examination, right? So that smaller test is essentially to validate whether the class has actually learned the problem. And that is your validation data set. All right. So, so that is your validation data set. So, I hope that made the problem clear. So you have your training set, you have your validation set, and your testing set. And many a time, the training and validation together is just known as the training data. Right? So different papers or different textbooks treat training, testing, validation differently. So so you can go ahead and depending upon that, you can select what explanation suits best. Right. So what happens essentially in machine learning is you iterate over these four steps, like pre-processing, machine learning, or learning, or iteration, and validation, until you arrive at a final model. Once you have arrived at a final model, you predict what outputs the model will give on the test data. And what you do is you retain your pre-processing steps from earlier. So the same pre-processing steps that you used before on the training data, you move them to the test phase without any changes, and you move your final model. So right now the model is fixed, its parameters are fixed, you do not really change anything, and see what the model predicts. So that is your final prediction. And then if you have some sort of metric, or if you have the actual prediction for the particular test case, then you can see whether the model, uh, how good the model is on the test data, right? So that is how there are three different accuracy parameters for each machine learning model. So you have your training accuracy, which is your accuracy on the training data. You have your validation accuracy, which is on the validation data. And then you have your testing accuracy, which is on the test data set. So if you are reporting anything in literature, then the accuracy that you should look at is your testing accuracy, right? So that is the accuracy which matters in the very end, and that is what you should be focused on. If your training accuracy will increase, because as and when the machine learning model sees more and more training data, it will, your training accuracy will be high. Your validation accuracy might be high on something or the other. So like on some data set, on some data points it might be good, on other data points it might be bad. uh, but your data set is bigger than both your validation data set. And finally, this is the accuracy value that matters. All right. So let us look at a supervised learning algorithm wherein we're looking at, predicting fuel economy. So, or predicting miles per gallon or kilometers per liter. Right. So this is a typical regression problem. And what we need to understand is we need to study the drivers of fuel economy. Right. So so the learning objectives for us is we want to build initial models without any coding, or with minimal coding if possible, and also see how we can do try out a bunch of models without So the first step will be loading our data into MATLAB, then using using say something like an app called the regression learner to run multiple regression algorithms, and finally arriving at a particular model. All right. So give me a moment to just switch to MATLAB. And so yeah. So in the meantime, let me just take up some questions which are there. Any similarities between machine learning and deep learning? So I hope the slide cleared that. Like, machine learning, deep learning is a subset of machine learning. Deep learning is end-to-end learning, wherein you do not do any feature extraction, whereas machine learning requires feature extraction. Right? So can't read labels. Yeah. So don't worry. I think it's more of the general concept, and we'll be sharing these slides with you, so you can go over the slides at the end. Um, yeah. So if the data set is corrupted, then how can we handle machine learning algorithms? So I think, yeah, some sort of data cleaning needs to be there. And how do you handle class imbalance? Okay. Yeah. So I think this is something that we can definitely address. So let's see, maybe if we can do that during this demo. Um, yeah. So can we record blood glucose levels only for one time for the entire day? No. So no. So you have to record it multiple times for getting values throughout the day. So yeah. And what is the training and testing data set? I think most data sets are the same because they're collected from the given to the machine learning model when training it, to allow it to recognize the pattern, while some data set is not shown. So similar to, I hope the classroom example, if you think of it, like you show some problems to a class when teaching it, you do not show other problems which are to appear on the end side. So you can, but the problems themselves can come from a single source, say a textbook, right? So think of it in that terms, and I hope that clears out uh, the thing. So what is the ratio for dividing the data sets? Yeah, we'll probably kind of just look at that when we open this. All right. So yeah, hopefully this is open. Yes. So this is the basic MATLAB interface. There are some questions on how to download MATLAB and everything. So we'll probably see if we can cover that briefly at the very end. Right. So yeah. So what I want to do is I want to look at the regression model, right? So if we go back to our presentation, so our goal is to predict or the fuel economy, right? Or the how many kilometers would a vehicle travel on a liter of petrol or a liter of diesel, right? Uh, so it's a regression problem. So what we'll do is we'll open up a regression learner app which is in there in MATLAB. So you can do this via coding, but I'll use the app-based workflow for now. So you just go to the third tab over here in apps, and you can go to the drop down and see regression learner. So if you just go and open up regression learner, so there's an entire bunch of apps for machine learning and deep learning. So on day 2, we saw the deep network designer. Here we'll be seeing the regression learner, right? So before we start, let's just have a look at how the data actually looks, right? So the data is there in this vehicle data XLSX. So I'll just open it outside MATLAB and show it to you. So it's a Excel sheet. So just there are 2 blank sheets. The entire data is in this one sheet. So there is some columns showing whether it's a car or a truck. There is the engine displacement, horsepower, transmission, the weight of the vehicle. I'm not sure what this is. The axle ratio, the city or highway driving, and the carbon emissions as well as the miles per gallon. All right, and we have to predict this variable using any of these inputs. Okay, so this is the objective, right? So what we'll do is either we can import this directly into MATLAB or have this mat file with the same data, right? So if I just open this mat data, so you'll see that I have this entire data set from here where where the origin of the vehicle, model year, this is slightly different. What I can do is I can import this as well. So import. If I just right click and import, so you can see that it imports this entire thing, and then you can either import these as individual column vectors, or you can import this as a table. All right, and you can also do a bunch of cleaning. I'm sure there are missing cells somewhere over here, right? So some data you might not have recorded the entire entry, so you can replace empty cells with a particular value, or replace empty cells in a particular column with a particular value, right? So what you can do is you can add more rules to it here and then import it. So if you click on this, like tick mark over here, it will directly import it into the data set as with a variable name vehicle data. And say if you're trying to do this over and over for multiple data sets, what you can do is you can import, you can create a script for doing this. So whatever changes you made here in this output type, any rules, all of these, if you generate a script or a function over here, it will create an entire script for doing the same thing that you did using the GUI. So that can be used if you are going to be doing this repeatedly for different data types. So if you're going to be doing this repeatedly, you can possibly generate a function, and otherwise you can generate a script to do this. All right. So I'll not save this. Yeah. Instead, I'll just go ahead and import it directly. So yeah. So now it says the following variables were imported: 2337 in cross 11. So there are 11 columns and almost 2,400 entries, right? So this is the vehicle data which is there. Now I have the regression learner app which is open. So I'll click on a new session, over here, and I'll select the variable input. So let me select the vehicle data which I had. Okay, so this is the input data set. Now, what is the response variable? In this case, I'm trying to the response variable is something that I'm trying to predict. So I can have a separate column, or I can as a response variable, or I can select one particular column from this data set itself as a response variable. So in this case, I'll select the output from output to be predicted from this table itself, from the data set variable, and my output is my miles per gallon, right? Because it's a value, so I'll select that. You'll see that some things were not displayed over here. Like out of the 11 columns, only 1, 5, 6, 7, 8 are displayed because the others are categories. And since this is a regression learner app, so only the ones which have numeric values will be predicted. So I'll go ahead and select miles per gallon. And what should I use for predicting the miles per gallon? So everything else, I'll select everything else as being used for predicting MPG. Right. So either I can choose to add all, remove all. So you can do that. If you click here, you can access documentation to see how you can prepare your data set. How do you clean data sets and so on. Okay. And then comes the validation. Okay, so you can perform. So as I said, you divide your input data into different sets. You perform your uh, into training, testing, and validation. Right. So again, validation can be of multiple types. So cross validation is something like you can divide your data into multiple groups. So this says 5-fold cross validation. So 5-fold cross validation is basically uh, you have divided your data into 5 groups. So if you have 100 measurements, say you are dividing them into groups of 20 measurements each, and each of the 4 of these you'll use for training, 1 for validation, right? So uh, that is one way of doing it. Another thing is holdout validation, right? So wherein like if you have a very large data set, what you can do is uh, you can choose not to show the model a particular percentage of the data set. So in this case, say the percentage is right now 25%, right? So what it says is like you have 75% of your data you show to the model, whereas 25% you do not show, or you hold this out. So that is your holdout validation. And then you can perform no validation at all. But if you do not perform any validation, then your model might overfit to the data. So what overfitting means is your model fits very well to your training data, but it does not generalize well. So, as in, your model is not general enough to predict miles per gallon for any sort of input. However, it is very specific, or it is very well fitted to only the training data. All right. So, let's go with simple cross validation for now. You can read more about validation through the link over here, right? I'll just select cross validation with a 5-fold one, and I'll start session over here. Right. So let me just make this a full screen. So as you can see, when I load the session, so my original data set comes over here, and my response variable is here. So I have a number of records and my response variable. So on the x-axis, I can change something like, say, the weight of the vehicle and how the response varies with that. So as you can see, there is some amount of trend in this, right? As the weight of the vehicle increases, my miles per gallon decreases. So for a vehicle with a weight of around 2,500 kilograms, my miles per gallon is something like 60. Whereas for one with around 6,000 kilograms, it's around 20, right? So, so basically, lighter vehicles have higher miles per gallon, right? So you can do all sorts of analysis initially using this. Let me look if there is any variation with the transmission type, right? So it's more or less flat, right? Depending upon, there are a bunch of transmissions: automatic, manual, number of gears, right? So 4-speed automatic, 5-speed automatic, 6-speed automatic, or manual, and so on, right? So let's see if axle ratio makes a difference. Somewhat. At higher axle ratios, it's generally lower, but it's largely the same. There is not really much variation over here. Uh, or engine to vehicle speed ratio. Okay. Again, there is a wide variation over here. City or highway. Yeah. So highway miles per gallon is higher than the city miles per gallon, right? So which is expected. Like bumper to bumper traffic in a city does not allow the fuel economy to rise a lot, right? So you can make all of these things. You can mark all of these things. You can study all of these things right initially before even starting to model. All right. Now, let us see something like, uh, you can select a bunch of features. So these were the features that you selected initially, but you can choose to leave some out now. All right. Um, you can do PCA on this to remove any redundant dimensions which is there. So you can either enable PCA, you can see how much of a percentage the PCA variation explains. So maybe you can kind of, we'll see what PCA essentially means in maybe later slides. And then you have a bunch of networks over here, right? Right from linear regression models to regression trees to support vector regression, Gaussian process regression models, or ensemble of trees. Right? So what you can do is, you have a bunch of models over here. So why I'm showing this is because, uh, you know, each of these is one particular regression model, right? So, uh, like, how do you kind of uh, select which model will perform best, right? So you don't know whether a fine tree will perform best or a support vector machine will perform best, right? And you may end up writing code from scratch for all of these. However, using this app in MATLAB will help you kind of, you know, run all of these models in one go just by selecting this. If you select this particular option, train all models, what it will do is it will use the same input data, same training, testing, validation settings, and train all of the models in this list for your particular task. Or you can select a smaller subset, like, all quick to train models, or you can select all linear models or all optimized, all trees to kind of to be run. So I'll just go ahead and select all quick to train models. Okay. And what I'll do is I'll use the parallel pool. So if you have multiple CPUs or a GPU associated with your laptop or computer, then you can use them to like accelerate your training. So right now I do not have any GPU on my laptop, but I do have 4 CPUs which are there, like a 4-core CPU. So what I'll do is I can enable parallel pools and use them to accelerate my training process. Okay, so let me just go ahead and train it. So what it will do is it will open the parallel pool over here. So this shows up a parallel pool. Okay, and yeah, and it will open this up and it will train this. Okay, so while it is being trained, let us see if there are any other questions. Okay, there are a bunch of answers from all of you on what is the sample size, what might be the training, testing, validation sort of uh, division. So yeah. So as you can see now, so your training, testing, and validation. So it's trained 4 models. Like so, it trained a linear model and a bunch of trees: a fine tree, a medium tree, and a coarse tree. Okay, and it found that a fine tree provided the least amount of error. All right, let me go ahead and train another, say, a quadratic SVM. Okay, and just train this. So if I simply train this, it will train on its own. So yeah. In the meantime, let's address this question. So there is no hard and fast rule about how much data you have to give for training and how much for testing and validation. However, like you can do 50-50, you can do 60-40, and so on and so forth. So what happens though is like a large amount of data is spent in training. So usually you have 60 to 70% of the data that you use for training, and this remaining amount you can use for validation and testing. So however, there is no hard and fast rule as such. So as yeah, so if I trained a SVM, I saw I saw that RMSE is even lower. The root mean square error is even lower. All right. So that means a prediction is more accurate using an SVM, right? So what I can do is I can go ahead and I can just see different plots over here, like So for the SVM model, this is my actual miles per gallon, the true response, while this is my predicted response, right? So ideally it should be along the 45-degree line. So ideally true response should be equal to the predicted response, but obviously there are errors in the prediction, right? So uh, so we can see errors in this case are much lesser. So let us look at the first linear regression model and maybe see what the error is there. Right. So you can see that the linear regression model predicts well for this, but it does not predict well for these cases, right? Whereas the SVM that we use was a quadratic SVM. If we had used a linear SVM, we would have probably ended up with something like this itself, right? So, so this linear SVM, linear regression is just a linear fit or a fit that you do. I think you can use Excel to do this and so on. But this is something that you can do. The quadratic SVM is something that you can do here, right? Then, in addition to this, uh, let's look at the residuals. So, residual is basically the error. Okay, so for the quadratic SVM, if you see, this is a bunch of like what is the error between your predicted response and your actual response. So basically, this gap, right, from this point to the 45-degree axis, 45-degree line rather. So we can see, like if you see this plot and this plot, you can see various similarities over here. Like so this is your true response. Whereas this is your predicted response. So if you see over here at say 80 miles per gallon, so my my true response is this much, whereas my predicted response was somewhere around 65 or something for these two particular points over here. So if I see the residual plot, so my true response was 80, while I predicted it by somewhere around if my true response was somewhere around 85, I predicted those ones as 65 or this, so these are my residuals which are there. Okay, so I hope that makes it clear. Following that, there is a MSE plot which currently does not appear. Let us go over that quickly. Okay, so instead of going residuals, let's go look at the predicted versus actual plot, or even the response plot over here. Okay, so maybe X can be your say your engine displacement, okay, or your weight. Yeah, or yeah. So if you just look at this plot over here, so you can vary your response plot by looking at various parameters, whereas say city and this highway, or say the carbon emissions which are there, and you can see what is your response, that is what is the miles per gallon that you actually predicted. So your blue markers are what were your true values. So for something, for a car which emitted 100 ppm of CO2, your response, that is your miles per gallon, was something like 85 miles per hour. All right. However, we predicted it to be for these values as somewhere around 65, the ones that we saw over here, right? So you get both your true values over here, your predicted values over here, as well as your errors as this um, red line over here, right? So basically, this is the error, this is the gap, right? And this gap is essentially the residual which is plotted over here, all right? So you can export all of these figures by going over here and clicking on save as, and so on and so forth. You can copy this, and if you're kind of exporting it, you can copy this as a picture or as a vector graphic and so on, right? Now what I want to show here is this advanced option, all right? So if we select the quadratic SVM and I select this advanced option, so the advanced option gives me something like advanced or tune advanced model, right? So it gives me an option for tuning different kernels. So I can select a Gaussian, linear, quadratic, or cubic. So, and along with that, different constraint modes, the kernel scale mode, these vary from model to model. So let me just go ahead and select something like, say a cubic model. All right. And I'll go ahead and close this. And so right now I just changed the kernel function from quadratic to cubic, and I'll train again. All right. So this should hopefully kind of reduce error even further, or I can see what happens. Okay. So yeah, so there are a couple of questions on how we can get error rate. So basically, in this case, it's a regression model. So your error is basically a root mean square error. So this is something that you can get here. Okay, this is taking a long while to train. So in the meantime, yeah, let's get back to the presentation and then maybe see what. Oh, all right, it just trained. So you can see the error reduced further when going from quadratic to cubic, right? 1.4 is the RMSE right now. All right. So you can, so right now, yeah. What another thing that I wanted to show here is optimization. So you can select, like, we got like a bunch of models like tree, fine tree, and coarse tree, right? So I can also select this option of, say, optimizable tree, right? So basically, if I select this, and I get like a bunch of optimizer options over here, right? So if I get a bunch of optimizer sessions or options, so basically what this does is it will optimize on different models and select the model which will give me the best result. Okay, so I can put in some sort of training time limits as well. And so I'll select Bayesian optimization right now. So we'll see why shortly. And so I'll select optimizable tree and click on train. All right. So what it is doing right now is it is optimizing a bunch of trees, and it is iterating on different hyperparameters. All right, or different parameters of the trees themselves. So as you can see, when we started off, without optimization. So the error was something like 4.6. As and when we optimized, so after the first level of optimization, the error came down to something like 3.3. After still further optimization, it is coming down to something like 3.15 or something. Okay, and we can let it optimize further. So I selected, like, you know, a bunch of parameters which led me to an optimization which provided me with an error of 3.15. All right, but I can definitely kind of predict, like use more, optimize more. Say if I wanted to optimize SVM models, I can select this and go ahead and do that. Right. So finally, once you've done all of this, what you can do is you can generate a function for this entire process that you did. You can export your final model. So let me go ahead and export this model of the SVM cubic model, okay, which because it gave me the least error. So I can export the model, or I can export a compact model, like, without the training data and all of that. So once I export this, I can say I can export it as trained SVM model, SVM cubic model. Okay. So now if I see back to the workspace, so you'll see that, I get like a model over here called trained SVM cubic. So if I just click on this, so you'll see that, I get a predict function over here, some required variables, and some about value, and then how to predict. So basically, to make predictions, use this function. Yfit is c.predict function p, where c is the name of the variable. So you can also see this over here, like how do you predict? So basically, if you want to predict, you can do this, right? You say yfit is c.predict function of p. So where your c is basically your trained SVM cubic model. All right. So I hope that gives you an overview of how you can use a do regression using MATLAB. Right. Let's get back to the presentation. And so this is the essence of what I was trying to demonstrate. So essentially, you will have to try out a bunch of models uh, for your regression or your classification tasks, and essentially all of those models will be wrong, but some of them might be useful. Some of them might give you errors which are within the acceptable range, right? So as this quote from a statistician named George Box goes, like essentially all models that you come up with will be wrong, but some of them will be useful enough for you to work with. All right. So if you want to kind of read more on where this quote came from, I highly recommend going over this paper, whose link I put in the presentation. So at this point, maybe we can just look at just taking a very short 1 or 2 minute break. Yeah. So if you just look at these particular comics, so machine learning is nothing but a bunch of linear algebra, right? So you're just varying that linear algebra until until your answers start looking right, right? So this is essentially what I was trying to convey in the last slide itself. Like, you just change your models until your answers start looking better, right? And we don't really want a machine learning model which kind of learns something like this, right? So if uh, this joke from like a concerned parent, like, which asks, like, if all your friends jumped off a bridge, would you follow them? So if you show this to a machine learning model, so the machine learning model is only seeing that all the friends are jumping off a bridge, and the machine learning model's response will obviously be yes. So we have to, even though you are using all of these machine learning models, you are using a bunch of machine learning models from the regression learner app or the classification learner, which we'll just see. It is up to you as the user to select a model which is useful, and it is like it is for you to make a common sense choice there, right? So otherwise, it will end up in a model which does the same thing as we outlined. All right. Yeah. So, anything else? How to deal with concept triple data misclassification? Okay. We'll probably see that quickly in the next example. Okay. So, or may yeah. Yeah. So the next thing is we'll look at a human activity identification. So this is a classification example, and our objective is to essentially classify human activity from the smartphone sensor, right? So we've already kind of outlined how it appears. So so if I just pause this video in between, so this is X, Y, and Z accelerometer data uh, acquired from a smartphone, and you can get this and we have here our actual class, that is say walking upstairs, and our estimated class over here, right? So if I have a different scroll to a different position, you'll see that if there is no activity at all, so that means the person is standing. If there is some amount of activity, then walking upstairs. Okay, if it's sharper, then it might be walking downstairs, and so on. All right. So, so how do we kind of process signals essentially when it comes to something like this, right? So what we have to do is we have to use buffers for deriving classifications out of signal data, right? So instead of deriving features from the signal, what you can do is one way is to use features from a signal. The other way is to create buffers and then use that as well. You know? So assume this is your signal. Say you have say 8 samples in your signal, all right? And what you can do is you can ask yourself these two questions, like how often do we need to do the prediction, all right? And how many data points do we need to predict, right? So how often do we need to do the prediction? Say you are looking at predicting something like whether a person is having a heart attack or not, right? So assuming like a person has a heart rate of something like 72 beats per minute, you will need to predict at least 72 times or at least 80 to 100 times a second, all right? In another case, like say if it is say predicting whether a room is hot versus cold, right? So those things can possibly take a longer time scale, right? So in this particular case, let us say that we need to predict every 2 samples, all right? uh, and then so we need to do predictions every 2 samples, and for each prediction, how many data points do we select? Like, so how many data points do we choose for each and every prediction? Right. So let us say for one prediction, we need 4 samples. All right. So what you do is you create buffers of 4 samples each. Right. So you create buffers of 4 samples. And since we need to predict every 2 samples, we need to create overlapping buffers. Right. So this is your first buffer. So you'll use x1, x2, x3, x4 to create your first prediction, to calculate your first prediction. And so this will be your buffer 1. Now you need to predict every 2 samples. So leave the first 2 samples, and now you take x3 to x6 as the second buffer and do the second prediction. And similarly, 5 to 8 as the third buffer and your third prediction. Right? And then you can compute features on each of these buffers or input the entire signal itself as a feature. All right. So let's look at this particular example, right? So if you're human activity detection using smartphones, so you will look at buffering, hyperparameter tuning, and our approach. Our approach will mainly be loading the data as we saw earlier, extracting some sort of statistical features from it, training a bunch of models, and training a machine learning model programmatically and optimizing the models. All right. So if you want to download this data, you can download it from this link over here, or you also have MATLAB Mobile, which is an application which is available for Android and iOS. So you can access your smartphone sensor data via the MATLAB Mobile app. If we have time at the very end, maybe I can show it quickly. All right. So let me just go ahead into classification models and open this. All right. So hopefully this is visible to you. All right. So this is a live script for the classification model. So I'll not download data. I'll use data which is already present here with me. So I've loaded this buffered data into my workspace. So I have already divided this into training, testing, and validation data. So my training data is something like this. So there is a 603 cross 4 array. So this is one. My training data is this, almost 6,000, almost 10 times of what my testing data is. And my validation data is somewhat more than training data, but yeah. So you can change this ratio depending upon what you feel like. Okay. Now, what I'll do is I'll go ahead and extract a bunch of statistical features from the data. All right. So in this case, my statistical features are my mean and my standard deviation. All right. So if I look at the training data, so if I look at the training data, so my training data will have like I can simply compute the mean and the standard deviation over here and have them into a bunch of features. Okay. Similarly, I can compute the same things for y and z direction data and read it into a variable. All right. So if I look at my final train features variable, this is what it will look like. Okay. So I have my activity value from here, and I have my mean, standard deviation for x, mean and standard deviation of y, and for z here. All right. Now, how do you kind of learn or train a machine learning model interactively? So what I did by opening up the regression learner app earlier, you can do the same thing by using the classification learner app from here. So the regression learner app is here, and there is a classification learner app for your classification task. Since here we have to categorize this data into different classes, I can open up the classification learner app from the apps tab over here, or I can open it from the like live script or command window itself by simply typing in classification learner. All right. And I'll input this data as for training and testing and validation. All right. So let me just open this up. So whatever you did programmatically or whatever you did in the GUI, that has a programmatic equivalent, or you can choose to do that, call the GUI from the program as well. All right. So now let's go ahead to the next one and run this. Okay. It's still running the previous model. Or let me import this from here. So this is okay. Yeah, this is currently not running. So what I'll do is let me just start it from here. So if I go to my training features, So my prediction variable is my activity over here, right? And which I'm trying to predict using these 6 features, the mean and standard deviation in all 3 directions. I get the same bunch of options over here, and I can just start the session. All right. And I can enable PCA and so on and so forth. And here, if you see, there is an option for providing misclassification costs, right? So in case, if you're doing some sort of, say, classification on ECG data, right? So if a normal ECG is classified as abnormal, that is okay, right? Because once if a normal ECG is classified as abnormal, maybe a doctor or a cardiologist, like they'll have a look at it and they'll say that okay, even though this is classified as abnormal, it is okay, it is still all right. However, in case an abnormal ECG is classified as normal, right? So that might mean missing out on treating a critical patient, right? So in that case, there is a higher cost involved in case of uh, if you're wrongly predicting your one particular class, that might be unsuitable for your machine learning model, right? So in that case, what you can do is you can assign misclassification costs from this tab over here. Okay. So misclassification costs are basically like a cost of uh, so yeah. If you see here, this is the true class and this is the predicted class. So basically you can assign costs for what if a particular class was predicted as the other. So in this case, there are no misclassification. It is equal misclassification cost assigned to everything. So everything has a misclassification cost of 1. And if you predict correctly, your classification cost is 0. You don't really have any costs, right? So, however, you can change this to kind of modify it to have misclassification cost assigned, right? It's simply a matrix which is taken into account when doing a prediction. All right. So I'll just go ahead and train this quickly. So as you could see, so this is the original set of features. You can vary these features to see what values come over here. So this is my original set. I can see just the data, or I can choose to see the model prediction as well. So right now I ran a tree, and it gave me accuracy of 90%. So if I just look at the, what values were predicted correctly, what classes were predicted correctly versus incorrectly, I can select this. So if I just look at the bunch of data, I can see that, this group and this group, that is the green and purple groups, lying down and sitting, are very well separated from the rest. Whereas walking upstairs and walking downstairs are very close to each other. The measurements are very close to each other. So it is obvious that, most of the errors might be concentrated around this region, right? So if I just look at the incorrect predictions over here, I'll see that, these are the values which were predicted incorrect. All right. So I can do the same thing by choosing to train a bunch of models over here and then generating, say, a confusion matrix for each of these. So a confusion matrix can be generated for each. You can generate true positive and false predictive values as well. And you can read more on this over here, right? You can also look at generating an ROC curve. So if you want to look at maximizing the area under this curve and looking at a operating point for you, then you can select this, and you can export your models as earlier, how I explained. You can also export these same figures out. All right. So if I just select this and maybe run train, let it run while we get back to the presentation and quickly wrap it up. All right. So, so the optimization that I was talking to you about is the hyperparameter tuning, right? So in the standard way, what you do is if there are 2 parameters in a particular model, you can do like a standard grid search and select which is an important parameter which will give you less uh, uh, accuracy, or which will give you more accuracy or minimum error, right? So instead of a standard grid search, a better method will be a random search through this entire search space, all right, to discover parameters faster. All right. And the best option to do that is Bayesian optimization. So Bayesian models, like there isn't enough time to go into this, but you can go through the documentation. And what you can do is you can select the optimizable trees over here, and you can select the optimization types over here. Yeah. So you can see instead of Bayesian optimization, you can do a grid search or a random search over here as well. All right. So I'll not run this, but as you can see, I selected a bunch of models, and then the KNN gave me a classification accuracy of around 96.8%. So I did not spend any time at all writing code. I simply imported the data. So the only code that I wrote was for calculating mean and standard deviation, right? So yeah. So so this is feature engineering. We'll not cover this. Um, so as you can, many of you might be aware of PCA, wherein you're doing some sort of analysis on what variables are important versus what variables are not. So what PCA does essentially is, like, say you have your measurements spread over these three variables. So you have three variables which you are measuring: X, Y, and Z coordinates, maybe, or X, Y, Z accelerations. And most of your measurements are falling along these lines. Okay. So what you can do is you can create a principal component, or say like a different axis system based on these. Based on the combination of this variable one, v1, v2, and v3. So your PC1 will be, say, some AV1 plus BV2 plus CV3, such that this line is defined in terms of that, and your PC2 will be similar. And now each of the principal, like each of the points or each of the measurements can be valued, or can be defined in terms of these two principal components. So what that helps to do is you just went from three variables to two variables and had the same level of accuracy because you're working on the same data set. All right. Unsupervised learning is basically clustering. You're looking at how close a particular data is for doing your machine learning. So I'll not cover this for now. So maybe I'll cover this in a couple of minutes. Yeah, and we're already on the top of the hour now. Yeah. So this is something that I wanted to show you. So much of it we've already covered. So, so what has happened in the machine learning world is, there is a bunch of data lying with corporations, with research groups, wherein we aren't really finding out any sort of features or any sort of meaning from that data. So and there is also a huge gap in terms of the workforce which is available to do this sort of task. So uh, so there is a huge amount of research effort being provided or being used for something called automated machine learning or augmented machine learning. All right. So what it essentially means is it will look at freeing up your task from selecting the optimal feature set as well as the optimal model, and instead like us as humans, or machine learning engineers, can focus more on solving more complex or difficult machine learning problems. All right. So we already saw a bunch of this in terms of model optimization. So the Bayesian optimization and parameter tuning that we saw was one part of it. The other part of it is how do we kind of automate the feature learning or feature processing or feature extraction tasks. All right. So in this case, instead of say for the human activity recognition, how we computed the mean and standard deviation, you can do a bunch of feature extraction using wavelets, using something known as the wavelet scattering framework. All right. So your auto machine learning essentially covers the middle two steps of your machine learning workflow, and you can do this in MATLAB as well. All right. So you can generate features using wavelet scattering and apply feature selection techniques like say PCA, whatever suits your model, and then optimize your model. All right. So in 2019 B, like till September or till March this year, you could train and optimize various models in the machine learner app itself. All right. Since 2020, we've put in a new feature called FitC Auto, all right, which can help you automatically select models for your machine learning algorithms. All right. So I'll not go into details over here. I'll just skip over this. So basically, what we're trying to do is, we found that uh, uh, like a bunch of features that were learned by deep learning models or deep neural networks look very much like wavelets or wavelet-like filters. All right. So what uh, what we took from the deep learning world and brought into the machine learning world is the exact same thing. So wavelet scattering is something which you can kind of bring to the machine learning world to extract features and give to the machine learning model for your for your optimal classification. All right. So if in case you do not have any features extracted from a signal or an image, you can definitely use the wavelet scattering framework to do that. All right. And if you want to read more on it, there is a IEEE PAMI paper from 2013 which explains what by uh, you can how you can kind of work with this scattering framework. All right. So without going into much detail here, what essentially happens is, if you have your signal or your image, you can directly input it to the wavelet scattering framework. In case of signals, your the function is wavelet scattering. In case of images, it is wavelet scattering 2. All right. And what it will do is it will create a bunch of features. The wavelet scattering framework will create a bunch of features which you can directly input to the classifier. All right. And get optimized results. So this is the same article link over here. And this is a pseudocode, so basically you have your wavelet scattering over a particular signal length, and you loop this over the entire signal. All right. Um, so there are a bunch of approaches for feature selection. I'll not go into detail here, but hopefully you can go over this and yeah. So as I said, you can integrate analytics, your data analytics, whatever your algorithms with other systems, right? So you can either deploy your data analytics systems to as standalone applications or web apps, or you can do your big data analytics in MATLAB and then interface it with a Hadoop or a Spark cluster. And you can also interface it with a bunch of other languages through something called the MATLAB production server. All right. You can run your data analytics without MATLAB using something called MATLAB runtime. And you can export your code and algorithm to embedded hardware as well. All right. So you can generate fixed point C, C++ code for different machine learning models, decision trees, ensemble decision trees. And if you're doing this on, say, for an IoT sort of application, wherein you have a bunch of edge devices which you are trying to do your classification or your data analytics on, then you can definitely, instead of writing code for each and every device out there, you can simply use MATLAB and Simulink for generating automated code. All right. And as I said, you can use MATLAB with a bunch of other languages, including Java, Python, C, C++, Fortran, and so on. All right. Or if you are integrating with different APIs, then you can do that as well. All right. And you can also call MATLAB from other learning environments. So if you're working with other other environments like Python or C, C++, you can call MATLAB from there and have it execute your code. All right. So I'll not go over this. I'll just summarize this slide and then close the presentation. So we saw how we can access and explore data through the data import panel. How we saw how we could pre-process it. So we did not see much in detail here, but you can definitely do this using a bunch of apps. We saw how we could do feature engineering. We focused mainly on the machine learning models, regression and machine learning, and classification apps, and looked at how we could do automated parameter tuning, high parameter tuning, or optimization, model optimization, and finally briefly overviewed how the various avenues which we have for deploying our machine learning models. Right. So if you want to, what can you do from here? So there are a bunch of on-ramp courses. So I had highlighted deep learning on-ramp in my previous lecture, but if you want to do, there is also a course on machine learning. So it's a 2-hour course available free of charge and no license is required. So it is available on the MathWorks website and it provides you with a course completion certificate. There's also a data science specialization with MATLAB offered at Coursera. So if you are interested in doing a longer MOOC, then you can definitely see this. There are a bunch of video series as well as ebooks as well as white papers on the MathWorks website, which you can possibly look over once I share these slides. And yeah, so let me just go quickly open this and show you where you can find most of these things. So if you just go to mathworks.com, on the landing page itself, you'll on the first link here is machine learning. So if you just click on machine learning over here, you'll get a bunch of options. You get a option for downloading a free trial. So if you do not have access, please use this for downloading a trial. And then there are a bunch of ebooks over here, user stories over here, and more examples, and something to test drive. If you want to test drive the classification learner app, you can click on this link and it will open up. And you can learn more about hyperparameter optimization and machine learning feature selection over this. All right, and code generation, and these are covered in these lectures over here. Right. If you're working with big data and you want to work with that, so you can use something called tall arrays to fit your data into your memory. So this would give you a good overview of how you can use tall arrays. Right. So the machine learning on ramp is free. So if you just search for machine learning on ramp, it will show up as the first result, and you can simply launch the course. And what I suggest is, in case you have a you're studying at a university, so sign in to your MathWorks account with your university email ID, and it will most probably, if your university has a license, it may give you access to longer courses as well. So which are 18 to 20 hours and so on. So always use your university email ID and sign in, and I think you might be able to get a few more courses from there. All right. Otherwise, the Coursera. So if you Coursera machine data analytics with MATLAB. So there is this practical data science course with MATLAB, which you can enroll in. So, yep. So that is all from my end. I'm sorry to have exceeded the time by 10 minutes. Yeah. So I don't see any other questions. Basically, how to choose an optimal RBF? I'd say go with the optimization workflows over there. Yep. So yeah. All right. In case there are no other questions, Tripti, then maybe I can stop sharing at this moment.
Yes, you can stop the sharing.
Sure. All right.
Thank you, Praful. Thank you very much for sharing your precious time, experience, and knowledge with us. So I hope for the future joining us in future any workshop or webinar. Thank you very much.
Sure. Yep. Thanks, Professor Murugan, again for inviting me. I'm happy to kind of talk to participants offline. So, in case, in case anyone still has questions, they can email me at ppy@mathworks.com, and I'll share these presentations with you. Thanks.
Yes, sure. Thank you.
Bye.
Bye.